Okay, please tell us something about the whispering gallery effect.
The whispering gallery effect in neutron scattering is an analog of a well-known effect in acoustics, and also of a less known but widely used effect for electromagnetic waves of broad wavelengths range. If a person speaks close to the wall of a round building, his whisper, his voice can be reflected from walls of this building many times. It can follow the surface, and another person on the other side of the building can hear him. Your whisper can even reach you, thus creating an effect of whispering gallery from where the name appears. Lord Rayleigh in the St. Paul Cathedral in London measured as experimentalist, as physicist, this effect for the first time, and the book which he published about this experiment and about the theoretical explanation of this effect was the first book after which acoustics as a science appeared. We measured an analogous effect for neutron scattering. You can see scheme of the picture, and I will explain it in more detail a little bit later. For neutrons, in contrast to sound, you have a massive particle. Therefore, you have not only whispering gallery modes, you have quantum states of these particles in the centrifugal potential. This phenomenon is similar to gravitationally bound quantum states also observed recently, and they both give an perfect example of so-called quantum bounce. It is curious that if you take these two effects together, centrifugal and gravitational quantum states, they provide you the first direct confirmation of the weak equivalence principle, equivalence of the gravitational and inertial masses for an object, for a massive object in the quantum state. If you want to have an idea how the experimental installation looks like, you can look to this picture. If you want to understand the experiment, you can look to this picture. We sent neutrons to a cylindrical mirror made of silicon single crystal. The silicon is very well polished. It has very, very good shape. And classically, neutrons can bounce many times from the walls, and you can measure them at the exit. In fact, this is not what is happening. In fact, neutrons, they feel close to the surface triangle potential, which is formed by repulsion of the wall, this side of the potential, and the effect of centrifugal acceleration, this side of the potential. As usually, inside potential, well, you have quantum states, which govern motion of the neutrons, and what you measure at the exit from this mirror, you measure interference between these quantum states.
Is there another important goal for this tour, this study?
Great. Characteristic size of quantum states we are studying is of the order of few times 10 nanometers, and one of the goals of our study is to look what is happening close to the surface at this distance. There are two different possibilities. Because quantum states, they can be deeply bound, low-lying quantum states. In this case, this is a kind of precision clock which is not affected by anything on the surface. Another case, when you have quantum states with energy which is close to the threshold, in this case, quantum states are extremely sensitive to the state of the surface. In the first case, we can search, for instance, for extra fundamental forces appearing due to new light bosons or due to some new physics. In the second case, we can study surfaces with accuracy which is much better than normal studies and more sensitive. Now, another point of interest that you can have perfect theoretical description of this phenomena. Therefore, if you see something on the top of precise theoretical description, then you might see a new phenomenon.
From the theoretical point of view, this is an amazing phenomenon through which one can feel the unity of physics. The theory of rigid poles, long ago designed for the high-energy physics, is nicely tailored for the neutron whispering gallery effect. Speaking about centrifugal states of neutron, we refer to the theory of quasi-stationary states. At the same time, we can look from another point of view and recognize here the theory of rainbow. The agreement between our experimental data and theoretical prediction is also amazingly good. However, the most exciting is slight difference between them, which, as we hope, can be attributed to new phenomena. We continue working on deep understanding of our results.